So in the video that I asked you guys to watch for Monday's class meeting, the purpose of that was to show you all that in a negative feedback op-amp circuit, we can apply the ideal op-amp rules and see that the behavior using the ideal op-amp is going to be extraordinarily close to what we would see using a practical op-amp model. So today we are going to look at several different commonly used negative feedback op-amp topologies, and we are going to use that ideal op-amp model in order to describe how these circuits work or how they process or synthesize an analog input signal. So I'm going to call this lecture Common Negative Feedback Op-Amp Circuits. And just as a very quick thing, I'm going to remind you of what the constraints are for an ideal op-amp. So if we have an op-amp, I'm going to put my non-inverting terminal on top, inverting terminal on bottom. So this is the voltage V plus. This is the voltage V minus. Here's our output voltage pin. Here is our VCC plus pin. Here is our VCC minus pin. There are a couple of different assumptions that we are going to make. Number one, we are going to assume that no current can flow into or out of the input terminals. So this means that this current, which I'm going to label I plus, must be 0 amps. And similarly, this current, which I'm going to label I minus, must also be 0 amps. And as we discussed, or as it was discussed in the last video, this is largely because of the extremely high input resistance of an op-amp on the order of mega ohms or larger. Our second assumption here is that there can be no potential difference between the input terminals. And a common way to state this, sorry, let me get this notification thing out of the way, is to say that our voltage present at our non-inverting input terminal V plus must be equal to the voltage present at our inverting input terminal V minus. As was discussed in the last video for the last class meeting, this voltage constraint comes about from applying negative feedback with a very, very large open loop voltage gain. Okay. A third assumption that we are going to make, this isn't really having anything to do necessarily with ideal op-amps, but we are going to assume that our op-amp circuits are biased such that saturation distortion doesn't happen. And what I mean by that, neglected, is that we are going to choose VCC plus so that it would be higher than any output voltage we might expect to see based on the application we're doing. And similarly, VCC minus would be chosen such that it would be much more negative than the most negative output voltage we would expect to see for our application. So since we're assuming that we are biasing or powering the op-amp correctly, I'm largely going to not draw the power supply terminals for these op-amp models, with the understanding that they do need to be biased correctly in order for the circuit to behave as we're discussing. So those assumptions / caveats out of the way, let's look at our first circuit. So I'm going to start with my op-amp. Most of the time, I'm going to draw the inverting input terminal on top for these cases because we're going to have negative feedback, and so it just looks a little cleaner to me. Here's our output voltage. And so what I'm going to do is I'm just going to tie my inverting input terminal to my output terminal using a wire. And then I'm going to apply my input voltage here at the non-inverting input terminal. So let me just label a couple of things here really quickly. This is V plus, this is V minus. Our voltage present at the non-inverting input and the voltage present at the inverting input respectively. So the first thing that we're going to do, and this is pretty much always going to be my first step, is to determine the voltage at the non-inverting input terminal. By inspection, we can see that V plus is equal to V in. Using our second ideal op-amp rule, we can then see that V minus must be equal to V plus, which is also then V in. And since there is a short circuit connecting our inverting input node and our output node, we can then say that V out is equal to V minus, which is therefore also equal to V in. So our overall relationship for this circuit is that V out is equal to V in. And another way that we could express this is looking at our closed loop voltage gain. So AVCL is going to be the ratio of the output voltage to the input voltage. And for this instance, that number is simply 1. So you may be asking yourself, why on earth would we bother making an amplifier that has a gain of 1, meaning that it does not, our input signal does not get scaled as it goes to the output. We get an exact copy of our input signal. This is what's called a unity gain buffer amplifier. Let me write that down. And this is an op-amp circuit that is used at the input stage of more complicated systems, particularly when the signal that we are trying to amplify isn't capable of driving a load itself, meaning that whatever source that we're using, so that could be some sort of piezoelectric crystal or sensor or something like that, is giving us a very small signal, and we want to make sure that the input resistance seen by that signal is incredibly large so that we don't lose any of the signal itself. So we use a unity gain buffer amplifier to provide that extremely high impedance or high resistance input stage. And then any power that's needed comes from the power supply terminals instead of the source itself. So this, again, this circuit is used very, very frequently as the input stage of larger amplifier networks. Okay. So our next circuit that we're going to look at is actually where this unity gain buffer amplifier comes from. So the unity gain buffer is a specialized version of what's called a non-inverting amplifier. So let me draw our circuit here. So we are going to have, actually, let me move this over just a smidge so that I have a spot to put another resistor. We're going to have our feedback resistor, which let's just call it R2. Here. We're also going to have an additional resistor. This is going to be R1, placed between the inverting input terminal and the ground. And we are going to apply our input signal to that non-inverting input pin. Okay. So just as a quick aside thing here, when R2 approaches 0 ohms and R1 approaches infinity ohms or an open circuit, this is a unity gain buffer. Really, we just need R1 to be significantly larger than R2, and we'll still get something very close to a unity gain buffer. But specifically, when we replace R2 with a wire and R1 with an open circuit, it is literally the exact same thing as a unity gain buffer. So for our analysis here, so again, we're going to find out what our voltage is at the non-inverting input terminal. Obviously, we just have Vn by convection once again, which means the voltage present at our non-inverting input terminal is also Vn. And what we're going to do now is we're going to apply Kirchhoff's current law at the inverting input node. So I'm going to add this current plus this current together. I am neglecting this current because we know, according to ideal op-amp rule number 1, that the current flowing into that input node has to be 0. So what I'm going to have is V minus divided by R1 plus V minus minus V out divided by R2 is equal to 0. And using a little bit of algebra and substituting in that Vn is equal to V minus, what we will find is that V out will be equal to 1 plus R2 over R1 times Vn giving us a closed loop voltage gain, AVCL, of V out divided by Vn is equal to 1 plus R2 over R1. So the gain of this amplifier is established by the ratio of the resistances that we use or that we bias this thing with, right? So when R2 is greater than R1, our output signal is a scaled or amplified version of our input signal. And as R1 becomes much greater than R2, our output signal becomes more and more like a copy, a one-to-one copy of our input signal. Okay. So this is a non-inverting amplifier. And it's used really in any situation where we want to ensure that we have a positive voltage gain, or we want to effectively form a resistor biased unity gain buffer, right? So the voltage gain for this particular amplifier can literally only be 1 or larger. So it can make a copy of our input signal, or it can make a larger copy of our input signal, but it cannot attenuate signals, it cannot invert signals or make them negative or anything like that. It's just capable of providing a voltage gain of greater than or equal to 1. Okay. For circuit number 3, all we're going to do is take this exact same circuit and we are going to swap where we apply our input voltage and where we apply our reference voltage or ground. Let's move this down to the next page. And remembering to give myself room here. Here is V minus and V plus. We're going to have that feedback resistor R2 yet again. We're going to have that resistor R1 placed connected to the inverting input terminal. But now, instead of applying ground here at this left leg, we are instead going to apply Vn. And for our non-inverting input terminal, instead of applying Vn, we are going to apply ground. Okay. So it's literally the exact same circuit that we just looked at, but Vn and ground have switched positions. So by inspection, we can see that the voltage present at our non-inverting input node is 0 volts, and therefore the voltage present at our inverting input node must also be 0 volts. Once again, we're going to apply Kirchhoff's current law, so we're going to add this current and this current together with the understanding that this current to the right must be 0 due to ideal op-amp rule number 1. And so what we're going to have is V minus minus Vn divided by R1 plus V minus minus V out divided by R2 is equal to 0. Recognizing that V minus is simply 0 volts, And doing a little bit of algebra, what we find is that our output voltage, V out, in this case, is negative R2 divided by R1 times V in. And therefore, our closed loop voltage gain, AVCL, will be negative R2 over R1. So this circuit is what's called an inverting amplifier circuit. And it is probably the most commonly used negative feedback op-amp circuit. It's used for a wide variety of applications, largely due to its versatility, okay? So what I mean by that is this circuit is capable of giving us a voltage gain with a magnitude greater than 1. So anytime R2 is greater than R1, our voltage gain is going to be large and negative. So we are going to change the polarity of our input signal, but we are going to scale it up. And anytime R2 is less than R1, we can also attenuate or make smaller. Our output signal will be smaller in magnitude than our input signal, but once again, we are also inverting the polarity of it, right? So in a lot of applications, the sign of our output signal doesn't matter one bit, particularly in simple audio signal amplifiers and things like that. Our output signal being 180 degrees out of phase really doesn't have any significant impact whatsoever on the behavior of the audio amplifier, because it's just going to be some time varying signal that's driving a speaker. So it doesn't matter. That 180 degree phase shift really means nothing, okay? But we can both amplify and attenuate with this thing. One of the questions that I get asked an awful lot about this circuit and the previous circuit is effectively how you can easily tell the difference between the two of them because they are so similar in structure. And the way that I usually tell my students to look at it, if the input signal is applied on the inverting input side of the amplifier, like we have here, it's an inverting amplifier. If the input signal is applied on the non-inverting side, like we have here, it's a non-inverting amplifier. It's literally that simple. It doesn't particularly matter if we had put some sort of resistor network between where we actually apply this input voltage and this non-inverting input pin. It'll make it a little bit harder to solve for this quantity V+, but the behavior in general will be the same. Okay. All right, so the next circuit that we are going to look at is a modification of this inverting amplifier. We are going to modify the circuit such that we have multiple input signals that our circuit is now processing in some way. So I'm going to take my op amp. Once again, here's my inverting input pin, my non-inverting input pin, and my output pin. Excuse me. I'm going to apply my negative feedback. In this case, I'm going to label this resistor simply F or RF for reasons that will be obvious in just a moment. And then I'm going to have a resistor between my inverting input pin and an output, just like we had a moment ago, I'm going to call this resistor R1. But now I'm going to put another resistor up here. Let's call this guy R2. And if we wanted to include more resistors, we could. And now I'm going to apply some input VN1. Give me just a second. This program is going to continue to give me this error until I restart it. So let me save this. Nope. So we're going to have an input signal VN1 applied at the left leg of resistor R1, and we're going to have an input signal of VN2 applied at the left leg of resistor R2. And we could add more resistors and more inputs if we needed to process more inputs. I'm going to ground my non-inverting input terminal. And now we're in a place where we can analyze things. Right? So by inspection, the voltage present at our non-inverting input terminal is 0 volts. So the voltage present at our inverting input terminal must also be 0 volts. Applying Kirchhoff's current law, I'm going to be adding this current plus this current plus this current together, where we know once again that this current is 0 amps. And so what I'm going to get is V minus minus VN1 divided by R1 plus V minus minus VN2 divided by R2 plus V minus minus V out divided by RF is equal to 0. Substituting in that V minus is equal to 0 volts and doing a little bit of algebra, what we find is that V out is equal to negative RF times VN1 over R1 plus VN2 over R2. So as I mentioned a moment ago, this circuit is simply a negative feedback, an inverting amplifier circuit, but now each individual input signal is being scaled by a specific ratio. It's the feedback resistor divided by the resistance associated with each input. Right? So this is what's called a weighted inverting summing amplifier, or a weighted inverting summer, right? If R1 is equal to R2, so all of our resistances that we're placing connected to the inverting input terminal and applying our input voltages at, then what we are going to get is that V out is equal to negative RF divided by, let's just call it R1, times the sum of VN1 plus VN2. So in this case, we no longer have a weighted summer because each individual input isn't being scaled by a separate scaling factor. Now the sum of all of our inputs are scaled by a single factor. So this is why it's an inverting summer. All right. The next circuit that we're going to look at is effectively an inverting amplifier and a non-inverting amplifier at the same time. So starting with my op amp, here's my inverting input terminal, my non-inverting input terminal, excuse me, my output terminal. I'm going to apply my feedback resistor, which in this particular case, I'm just going to label as R. I'm going to use an identical resistor here. So this one is also R. And I am going to apply my first input voltage here. And now I'm going to establish what is effectively a simple voltage divider network at the non-inverting input terminal. So what I mean by that is I'm going to place yet another resistor R here, and then a fourth resistor R here, and apply a voltage VN2 at this level. So this is the first circuit where it's not extremely obvious what our voltage V plus is. So I'm going to tell you here that V plus in this case will be VN2 divided by 2. And I'm going to explain that, hopefully pretty straightforwardly, by observing that all of the current that leaves our input voltage source 2 has to flow through resistor R in the horizontal position, and then flow through this resistor R in the vertical position, like so, in its path to ground, because we know that none of it can split off and flow into this input node. So the total voltage drop across those two resistors is R, so it should split evenly between them due to the principles of voltage division. Since those two resistors are identical, exactly half of the voltage will appear at the non-inverting input terminal. So with that out of the way, we could then say that V minus will definitely have to be the same as V plus. So this is also going to be VN2 divided by 2. And now we're going to apply Kirchhoff's current law here at this node, with the understanding that the current here is 0 amps. And so what we're going to get is V minus VN1 divided by R plus V minus V out divided by R is equal to 0. We could then, so I'm going to actually talk you through the algebra here a little bit. We can see that there is a common factor of 1 over R. So if we multiply both sides through by 1 over R, we get rid of this. And now substituting in our relationship for V minus, we have VN2 over 2 minus VN1 plus VN2 over 2 minus V out is equal to 0. Adding our like terms together, we have VN2 over 2 plus VN2 over 2 just gives us VN2, minus VN1 will be equal to V out, and this is our relationship. So this is what's called a differencing amplifier, because it simply takes the difference of two analog input signals. This is another thing that's commonly seen as an input stage. This doesn't provide any amplification or scaling whatsoever. It simply gives us the difference between two signals, and then we could further scale it by cascading this particular amplifier circuit into a stage with a voltage gain. Yeah. So put a box around this guy. So what we've seen thus far is that we can copy an input signal. That's what our unity gain buffer does. We can amplify or scale up our input signal. That's what a non-inverting amplifier does. We can scale up or scale down an input signal using an inverting amplifier. We can effectively add and scale input signals using a inverting summer. We can subtract input signals by using a differencing amplifier. And so now we're going to talk about the last two mathematical operations that we can do using a single op-amp circuit. We cannot do multiplication or division, but we can actually do calculus. We can do integrals of input signals and differentiate input signals using a single op-amp circuit. So both of these circuits that we're going to talk about here are really just inverting op-amps where we are replacing one of the resistors with an energy storage element. Okay. I am going to happen to derive these relationships using capacitors, but you could just as easily implement these using an inductor. In practice, capacitors are usually used just because the tolerance on a capacitor, so its value with respect to the nominal value listed, is usually a bit higher for capacitors than it is inductors, meaning that if you get a 47 nanofarad capacitor out of a bag or whatever, it's probably going to be pretty close to 47 nanofarads. Whereas if you've got a similarly sized inductor, the value of that inductor could be significantly more off. Okay. All right, so I believe this is circuit number 6. And I am going to, in this particular case, replace that resistor R1 with a capacitor for our inverting op-amp configuration. So here is V plus, here is V minus, here is V out. Since I'm only going to have a single resistor in this circuit, I'm just going to call this guy R up top in the feedback position. And then I'm going to put a capacitor here. My input voltage is going to be applied at this node, and I'm going to specify here that Vn will be some time varying signal. And I am going to ground my inverting input node. Right. So a few things here. We are going to use effectively the exact same steps that we've been doing to analyze or describe the behavior of all of these. But I'm going to refresh you on a couple of quick relationships. The first of which is that the current flowing through a capacitor, IC of t, is equal to C times the derivative of the voltage drop across the capacitor with respect to time. And then we also have the inverse of this relationship, where we can say that the voltage drop across the capacitor with respect to time is 1 over C times the integral from negative infinity to some point in time we're interested in of the capacitor current with respect to time. So just for purposes of this analysis, I'm going to define my capacitor voltage Vc of t with this particular polarity, so positive polarity on the left. And I'm going to define my inductor current, IC of t, as follows, where the current is flowing into the positive polarity terminal. Okay. So we can see very easily that the voltage present at our non-inverting input terminal is simply 0 volts, which means the voltage present at our our inverting input terminal must also be 0 volts. I'm going to apply Kirchhoff's current law again. I'm going to do it a little bit differently, just based on the direction of IC of t that I've established. So I'm going to say that IC of t is flowing into this node, so it must be equal to this current flowing out. Since we know that this current is 0 amps, so my Kirchhoff's current law relationship is simply IC of t is equal to V minus V out divided by R, which, don't know why I switched to blue there. I can rearrange that to say then that V out, and this will be a time varying signal as well, will be negative R times IC of t. And using one of my relationships from up top here, I can say that then we would have negative R times C times the derivative of my capacitor voltage with respect to time. Well, what I'm going to do here is I'm going to explain, hopefully illustrate a bit, why in this particular circuit, Vn and Vc are literally the exact same things, right? So if I represented Vn of t as a voltage source, I could see very explicitly that the positive polarity terminal of both Vn and Vc are at this node. The negative polarity terminal of Vn is at ground, and the negative polarity terminal of Vc is at V minus, which is 0 volts, or effectively the exact same voltage as ground. So Vc of t and Vn of t represent literally the exact same signal. Therefore, V out can be given as negative RC times the derivative of our input voltage with respect to time. So this is what's called a differentiating amplifier. For the purposes of our class. I say that because this exact same circuit is a fundamental building block of communications networks. It is in a frequency domain, I believe this is going to be a high pass filter, but I might be mistaken there. It is also used in control systems as a fundamental building block. So this circuit you're going to see over and over again in your electrical engineering classes, used in a variety of different domains, but it behaves the same way every time. It's just the perspective by which we're looking at it, right? So in the time domain, this is performing differentiation. In the frequency domain, this winds up being a filter of some sort, and control systems as well. Okay. All right, so our last circuit is going to be the exact same circuit that we just looked at, but now we are going to swap the position of the capacitor and the resistor. All right, so this is circuit number 7. Starting with my op amp. I have my inverting input terminal, my non-inverting input terminal, my output terminal. Now I'm going to place my capacitor in the feedback position. And I'm going to place my resistor here. At this left leg is my input voltage. And I ground my non-inverting input terminal like so. So we can see by inspection that our non-inverting input voltage is 0 volts, which means our inverting input voltage is also 0 volts. Oh, sorry, really quickly here. Let's define our capacitor voltage having this polarity and our capacitor current having this direction. So applying Kirchhoff's current law here, I'm going to have this current flowing in will be equal to the current flowing out of the node, with the understanding that this is 0 amps. So from here, we can see that we would have Vn minus V minus divided by R is equal to IC. Or since V minus is 0, actually, let's rearrange this really slightly. We could see that IC is equal to Vn divided by R, right? So now I'm going to use my integral relationship between capacitor voltage and current. So since I have a well-defined IC of T, I could say that my capacitor voltage, Vc, is 1 over C times the integral from negative infinity to T of Vn T over R dt, or 1 over RC, since my resistor value is a constant, times simply that integral of Vn. So what we just found here is that the capacitor voltage is equal to this. So what we need to do now is relate our capacitor voltage to our output voltage. So once again, I'm going to do something here to help illustrate what that relationship is. Our output voltage is measured with respect to ground. So the positive polarity terminal of our output voltage is at the same node as the negative polarity terminal of our capacitor voltage. And the negative polarity voltage of the negative polarity terminal of our output voltage is at ground. The positive polarity terminal of VC is at ground. So what this means is that VC and Vout are equal but opposite in polarity. So we could write this as, negative Vout of T, and rearranging, really just moving the negative sign to the opposite side, we find that our output voltage Vout is negative 1 over RC times the integral from negative infinity to T of our input voltage with respect to time. So this is our integrating amplifier, because the output is a scaled version of the integral of the input signal. Now, realistically, we don't know exactly what the capacitor was doing at T is equal to negative infinity, right? So when we have an energy storage element, we need to be a little bit careful here. So I'm setting these limits of integrations to be from negative infinity to say that the capacitor doesn't have any energy stored. One way that we could physically force this to happen, and this is how it's done practically, is we would usually put a resistor in parallel with the capacitor to give our capacitor a fixed discharge path and ensure that it has no stored energy at the beginning of our cycle. This will very slightly change the system response. It's not wildly difficult to look at in the time domain like we're doing things here, but it'll be much easier to look at in the frequency or Laplace domain, which is how we look at circuits in circuits 3. So I'll wait to get into the nitty-gritty details of that analysis until later. So we have talked about 7 different negative feedback op-amp circuits that you will be expected to be able to identify and describe the behavior of. If you have any questions, I would be happy to answer them. If not, I will see you all in class for Friday, where we are going to talk about cascaded op-amp circuits, or what happens when we chain multiple op-amps together.